And good evening, everybody. As Bodhi indicated, this is already session 21 in our series. I'll talk about gravity loads today, wind loads tomorrow, and then starting on Wednesday, I have 8 lectures on the earthquake-resistant design of structures. So the materials courses, concrete, steel, are behind you. I think that the gravity and seismic design may be more interesting. I don't know. You will have to tell me. But anyway, we are entering into a different phase of the training program. The entire presentation today is based on BNBC 2020. Very occasionally, I have brought in either ACE 705 or in a couple of cases IBC. In your case, it will be the 2009 edition of the IBC, but largely I have avoided that. The entire presentation is really based on BNBC 2020. Gravity loads are given in part 6, chapter 2, but in part 6, chapter 1 of the code, there are some provisions related to gravity loads. So I did want to bring that to your attention to start with. The loads themselves are not given here. They are in chapter 2, but there are some provisions related to gravity loads in part 6, chapter 1. There is section 1.4 titled Design for Gravity Loads. Under that, you see the subdivisions are general, floor design, roof design, reduction of live loads, very important topic directly related to the live loads given in chapter 2, but it is placed here for reasons I do not know in section 1.4. Posting of live loads, that is sometimes required in a building. Restrictions on loading, special considerations, deflection, and camber. Then there is design for miscellaneous loads, section 1.6. Under that, general, self-straining forces, stress reversal and fatigue, flood, tidal or storm surge and tsunami, rain loads, other loads. So this is all in chapter 1, and then under 1.6 miscellaneous load, particularly 1.6.6 other loads, these other loads are itemized. Not a whole lot is said here, but the main thing that is done in chapter 1 is you are referred to the chapter 2 section where the code talks about these particular loads. So temperature effects discussed in 2.6.4, soil and hydrostatic pressure, impacts and collisions, there aren't really any provisions. There is a little, not really, there is really no provision. This is why no section number is referenced. Explosions, fire, vertical forces on air raid shelters. There are all kinds of provisions on fire, but fire loads, there are no provisions. So there is nothing listed, no chapter 2 section number. Loads on helicopter landing areas, erection and construction loads, moving loads for crane movements, creep and shrinkage, that is listed under loads, dynamic loads due to vibrations, and construction loads. This is a repeat of erection and construction loads. So I don't find this list particularly well thought out. But anyway, it draws your attention to things that are at least sometimes important. Now, before going to chapter 2, I thought I would go over with you section 1.9 of the code, although it doesn't at least directly have much to do with loads. And I decided to do that because BNBC is these things are what is covered in 1.9 is typically said in most building codes, but BNBC goes into details that are rather uncommon, including how the drawings, the scale of the drawings and things like that. In any case, it would be very good of you to recognize that these requirements are in BNBC. Most people tend to go to, the loads chapter or concrete design or steel design, directly without paying much attention to the front part. So, every building or structure designed shall have its design documents prepared in accordance with the provisions of 191. We are in section 1.9, the minimum requirements for design review and construction observation. So we are talking about two things, design review and construction observations shall be those set forth under 192, 193 respectively. Okay, so design documents prepared in accordance with 191, design review in accordance with 192, construction observation in accordance with 193. This is 191, the design documents. Design documents shall be prepared and signed by the engineer responsible for the structural design of any building or structure intended for construction. Okay, whoever has designed the structure will sign the drawings. The design documents shall include, this is very important, this level of detail is not particularly common, but you are lucky, the code is very detailed in these regards. The design documents shall include design report, material specifications, and a set of structural drawings. Okay, so drawings and specs are always included in design documents, but BNBC specifically calls for a design report, which shall be, so the report, the specs and the drawings shall be prepared in compliance with 192, 193 below for submittal to the concerned authority. So for most of you, the concerned authority will be RAJUK, but then there are other authorities in places like Rajshahi or Khulna. Outside of the authorities, there are how should I say? There are entities to which you should be making your submittal. Okay, there is actually, depending upon where you are, it may be municipality, it may be PWD, executive engineer. These things are laid down, and there is no confusion about that. So the concerned authority is what BNBC says. The concerned authority, as I said, for most of you will be RAJUK. For the purpose of this provision, 191, design documents, the concerned authority shall be either persons from the government approval agency for the construction, this is what I was talking about, or the owner of the building or the structure, or one of his representatives. This last part I find to be kind of surprising. Submission to the owner of the building. So the designer will prepare the design documents and submit them to the owner. That doesn't Until they are submitted to the concerned authority, you will not get the construction permit to proceed. So this last part, the concerned authority may be the owner. I do not fully understand unless the owner is the government, a government agency like the PWD. So I don't quite know the last sentence, what it means. The design report shall contain the description of the structural design with basic design information as provided below. That there is a list, pretty detailed list, which I will not go into, so that this is important. So the design report, you remember, there is a report, then the specifications, and then the drawings. The report shall contain the description of the structural design with basic information as provided below. There is a list, so that any other structural design engineer will be able to independently verify the design parameters and the member sizes using this basic information. So somebody else should be able to verify your design based on the information you provide in the report. The design report shall include but not be limited to the following. As I said, I didn't go into the list. The structural drawings shall include but not be limited to the following. There is again a long list in BNBC. Okay. So the report, the specs, then the drawings. Okay. Then we talked about, so that those are the design documents. Then we talked about design review and construction observation, remember? So this is design review in 194. The design documents shall be available for review when required by the concerned authority. Shall be available for review when required. Review shall be accomplished by an independent structural engineer, independent of the designer, qualified for this task and appointed by the concerned authority. So the reviewer shall be appointed by the concerned authority. Design review shall be performed through independent calculations. That's what the code says. Based on the information provided in the design documents prepared and signed by the original structural design engineer to verify the design parameters, including applied loads, methods of analysis and design, and final design dimensions and other details of the structural elements. This is pretty uncommon as a code requirement, that the reviewer shall do his or her own calculations to verify the design. That is not typical. Typical is the reviewer goes through the drawings, sometimes or oftentimes goes through the design calculations. But except for here and there, the reviewer does not do his or her own calculations. Unless in doubt, he doesn't do that. The reviewing engineer shall also check the sufficiency and appropriateness of the supplied structural drawings for construction. That is very important, actually. Yeah, sufficiency and appropriate. Okay. Construction. So that was design review. Now it is construction review or construction observation. So construction observation shall be performed by a responsible person who will be a competent professional appointed by the owner of the building. Now the owner appoints the construction observer, as he is being called here, not the jurisdiction, not the authority. Okay? So appointed by the owner of the building or the structure. Construction observation shall include but not be limited to the following. Okay, construction observation shall include specification of an appropriate testing and inspection schedule prepared and signed with date by the responsible person. Appropriate testing and inspection schedule. Review of testing and inspection reports and regular site visit to verify the general compliance of the construction work with the structural drawings and specifications. So all of that is very important, but I want you to clearly understand that here the code is talking about testing, inspection, etc. by the owner's inspector. There is also, very importantly, inspection by the jurisdiction. In your case, RAJUK inspectors. That is on top of this, that is in addition to this. Both need to happen. So the owner needs to make sure of adequate testing, adequate inspection, and the owner needs to make sure that what is built is what was designed at the design office, as opposed to something else, which does happen quite often. But in addition, the jurisdiction cannot leave it all to the owner. The jurisdiction has independent inspection almost always. Okay. So that brings us to part 6, chapter 2, where the loads actually are given. This chapter has an introductory section, then it talks about dead loads, live loads, wind loads, earthquake loads, miscellaneous loads. Under that, there are quite a few things. And then combinations of loads. You design your structure for combinations of loads, not for just one load. And I will take you through section 2.7, load combinations, before I get into the loads themselves. I think it's better that way. You see what you do with the loads in design. Okay, under miscellaneous loads 2.6, these are the ones listed. So rain loads, loads due to flood or surge. And I said that Dhaka metropolitan area is largely unaffected by that. You are hopefully not all from the Dhaka metropolitan area, I do not know, but the overwhelming majority of you are from Dhaka metropolitan area, and for you, the flood and surge are not significant concerns. Temperature effects, soil and hydrostatic pressure, loads due to explosions. I said that that's a specialized topic that we would not go into. Vertical forces on air raid shelters, also very specialized, and loads on helicopter landing areas. Erection and construction loads, that I find it pretty surprising that BNBC talks about them, because the erection and construction loads go under what we generally describe as means and methods of construction. Means and methods of construction. And those are typically not covered by building codes. There are other documents, but anyway, BNBC has seen fit to talk about erection and construction loads, not in all the detail that you need, but anyway, that is a topic in the code. Okay, so the introductory part of chapter 2. This chapter specifies the minimum design forces. That word minimum is very, very important. You have to design, at least for the loads that are given. You can go higher, you cannot go lower. Okay, so this chapter specifies the minimum design forces, including dead load, live load, wind and earthquake loads, miscellaneous loads, and their various combinations. These loads shall be applicable for the design of buildings and structures in conformance with the general design requirements provided in Chapter 1. I didn't get into them, but there are general design requirements. A few things will come up as we discuss the load combinations. Now, there are limitations that are spelled out in BNBC in black and white. Okay, and this may be worthwhile taking a look at. Provisions shall generally be applied to majority of buildings and other structures covered in this code, subject to normally expected loading conditions. Okay, so provisions shall apply to normally expected to buildings that are subject to normally expected loading conditions. For those buildings and structures having unusual geometric shapes, response characteristics, or site locations, so unusual geometric shape, unusual response characteristics, or site locations, or for those subject to special loading, including tornadoes, special dynamic or hydrodynamic loads, etc., site-specific or case-specific data or analysis may be required to determine the design loads on them. So then you have to go beyond the code. You may require local data. Okay, so the code is for buildings subject to normal loads, or whatever normal may be. Okay. So in such cases where you have to reach out, and all other cases for which loads are not specified in this chapter, loading information may be obtained from reliable references, so that's one possible source, or specialist advice may be sought. However, such load shall be applied in compliance with the provisions of other parts or sections of this code. Once you have the loads, you do your design according to this code. Chapter 2 has terminology and symbols and notations. I mentioned that because particularly terminology is very, very important. Okay? Definitions of terms used in the code. Through the years, you would not believe how many code-related questions we get at our office. Okay? People have all kinds of questions. And I have seen through long experience that a significant part of those questions would be answered if the questioner simply looked at the terminology given in the code. Those definitions of terms are extremely important. If you look at them, if you understand them, many questions go away. Okay, so please pay attention particularly to terminology, and symbols are also extremely important. It tells you precisely what you are dealing with. Okay, so as I said, I will discuss load combinations before the loads. Load combinations are in section 2.7 of the code. 272 is allowable stress design, 273 is strength design. Okay, I'll show you both. And then load combinations for extraordinary events is in 274, and load combinations for serviceability is 275. That itself is unusual. In no US code are you going to see load combinations for serviceability. I do not know how many other countries have them, but anyway, you have a separate section titled Load Combinations for Serviceability. I am not exactly sure if that is a help or maybe partly confusing. I do not know. I would leave that to your judgment. But in any case, there is a whole section on load combinations for serviceability, And of course, I will take you through that section. Okay. Now, the next thing, I cannot tell you how important this is. And talking about the questions that we get through the years, this is one of the most recurrent ones. The question comes in various forms, but the basic question is, people would ask, you know, how do we combine dead and live loads which are acting vertically down on our structure with wind loads which are acting sideways? How do we combine these loads? Very basic question. How do we combine gravity loads which are acting downward with wind loads which are acting sideways? And the answer is that we don't. We have never ever combined or even tried to combine gravity loads with wind loads. That's not what we do under load combinations or in design. What we do is gravity loads, let us say dead loads, cause bending moments, shear forces, axial forces in various critical sections of various structural members. So do live loads. Live loads also cause bending moments, shear forces, axial forces at the same critical sections of the same structural members. So do wind forces. Wind causes bending moments, shear forces, axial forces at various critical sections of various structural members. Those bending moments due to dead loads, live loads, wind loads can be combined. Those shear forces due to the various loads can be combined. And that's what we do in design. We combine load effects, the internal forces caused by the loads, the bending moments, the shear forces, the axial forces. We do not combine the loads. Okay, so combination of load. So when we talk about load combinations, we are really talking about combination of load effects, combination of internal forces caused by external loads, such as bending moments, shear forces, axial forces. Okay, so these so-called load combinations are not load combinations at all. Okay, that's extremely important, that you absolutely must remember the rest of your professional life. Okay, so this is kind of an illustration of that. Okay, so in the first picture you are considering dead loads, and on that particular beam the dead loads cause this kind of shear forces, and so these are the bending moments caused by the dead loads on that particular beam. These are the shear forces. If we consider earthquake loads on the same frame and consider the same beam, the earthquake forces cause shear like this and bending moment distribution like that. Okay, so when we combine the bending moments caused by dead loads and earthquake forces, we get a bending moment distribution as shown in the upper picture. And when we combine the shear forces due to dead loads with shear forces caused by earthquakes, we get a shear distribution as shown here. When we combine the bending moments due to dead loads with the bending moments caused by earthquakes, we get a bending moment distribution as shown in the lower picture. And those would be the basis of design of that particular member. Okay? So combined load effects. Okay, buildings, foundations, and structural members shall be investigated for adequate strength to resist the most unfavorable effect resulting from the various combinations of loads provided in this section. So you have to consider multiple load combinations in the design of a structure. The combination of loads may be selected using the provisions of 272, that is allowable stress design, or 273 strength design, whichever is applicable. Okay, you in concrete you don't have a choice anymore. It's all strength design, but in the other materials you still have a choice. You can use ASD or strength design. Then something very important this side. However, once 272 or 273 is selected, allowable stress design or strength design is selected for a particular construction material. So you have a structure in which you have parts constructed in masonry, parts constructed in wood. You have decided that you will do the masonry design by the strength design method. Okay, you have to stick to it for all masonry members. So once allowable stress design or strength design is selected for a particular construction material, it must be used exclusively for proportioning elements of that material throughout the structure. All masonry members must be designed using strength design. But the wood members can be designed, if you like, using ASD. But then all wood members must be designed using ASD. In addition to the load combinations given in those two sections, any other specific load combinations provided elsewhere in the code shall also be investigated to determine, etc. So there are things said elsewhere in the code that you may have to consider. Then something that is also extremely important. Now, what is said here is repeated later when it comes to strength design. And I do not understand why they have said the same thing twice. It's probably just sloppiness. Anyway, I will show you the other place. The most unfavorable effect of loads may also occur when one or more of the contributing loads are absent or act in the reverse direction. This is extremely important. Most unfavorable effect may occur when one or more of the contributing loads are either absent or act in the reverse direction to that of the other loads. Okay, so it goes on. This all makes a lot of sense. Loads such as F, H, or S. F is the fluid pressure, H is horizontal earth pressure, S is snow, shall be considered in design when their effects are significant, not otherwise. Otherwise, you get floor live loads shall not be considered where their inclusion results in lower stresses in the member under consideration. Okay, if live load not being present is more critical, that's what you should consider. And live loads may or may not be there. If it's not being there is more critical, that's what you should consider as basis of design. The most unfavorable effect from both wind and earthquake, this is also important, the most unfavorable effects from both wind and earthquake loads shall be considered where appropriate. Okay, so if you're in a place that is subject to both earthquakes and obviously every place there is wind, but where there is an earthquake hazard, you shall essentially consider both, but not both at the same time. Okay, you shall design for wind, you shall also design for earthquake, but there is no load combination where you combine wind effects with earthquake effects. That you don't. Okay? They need not be assumed to act simultaneously. Okay, so these are the ASD load combinations of BNBC 2020. Okay. The DF, okay, so let us look at that. D is dead loads or dead load effects. E is total load effects of earthquake. E is a pretty complex term. it is made up of two parts: horizontal earthquake effects, vertical earthquake effects. I will go into those details in probably the second earthquake segment. Okay, so that I will refrain from discussing today, but for now, two things. One I just said, another I did not say. E is a strength level force. So in strength design load combinations, the load factor on E is 1.0. In ASD load combinations, you have to bring the strength level earthquake force down to service level. And that we do by dividing by the load factor that used to be common in seismic design in the days when earthquake forces were specified at service level. That load factor was 1.4. Reciprocal of 1.4 is 0.7. So in ASD, you will typically see a load factor of 0.7 on E. Okay. Secondly, as I said, it is made up of two parts. It consists of horizontal earthquake effect and vertical earthquake effect. So quite a bit to be said about E, which will come next week. F, loads due to weight and pressures of fluids with well-defined densities and controllable maximum heights. F, very specific. F sub A, flood loads, very difficult term to come up with, as I'll discuss a little bit later on. H, loads due to weight and pressure of soil, water in soil, or other materials, or related internal moments and forces. So typically I call it horizontal earth pressure. That's what it is. And that includes the weight of the water that is in the soil. Okay. L, live loads. L without a subscript is floor live load. L sub R is roof live load. Capital R is rain load. T is a difficult term. It is T, I think, stands for temperature effects, but it is the best way to describe T. It is the effects of restrained volume changes. Restrained volume changes. Okay, volume change may be because of temperature rise or fall, or volume change may be because of shrinkage. Water, as water evaporates out of the concrete, it shrinks. If the concrete is allowed to shrink, there is no problem. There is a little bit of shortening, but that typically is not an issue. The problem is when it's not when concrete structural members, at least in cast-in-place construction, are monolithic. A beam will frame into columns or walls. So when the beam wants to shorten because of shrinkage, the columns or walls that the beam is framing into will not let it shrink. And that is a problem. When something wants to shorten and you don't allow it to shorten, you are in fact pulling on it. And that will set the concrete in tension. Concrete is weak in tension. So you are now looking at cracking. And unless you have provided adequate reinforcement, the cracking may cause very serious problems, including failure. Okay, so T, the effects of restrained shrinkage, restrained volume changes have to be taken seriously. Okay, T. W is the effects of wind loads. Okay, so that is, those are all the terms that there are in this equation. So, so this is dead load and fluid. Let me let me maybe go to this simpler version where we have dropped the F, H, and T. Okay? Remember, those things have to be considered only when they're significant. So when we are dealing with just dead load, live loads, wind, earthquake, and rain, these are the ASD load combinations. Okay? Just dead load, dead plus live, dead plus roof live load or rain load, we consider the worst of the two. Dead load, live load, roof live load or rain. This involves wind or earthquake. This is wind or earthquake. Then this is counteractive, dead load counteracting wind and dead load counteracting earthquake. Remember, the load factor on E is 0.7. Okay. The load factor, okay. I don't know that I have anything else to point out. Okay. So these are the ASD load combinations. The only other thing I might say is we typically refer to these as additive load combinations. Dead load causes bending moment in the same direction as the bending moment caused by wind or earthquake. Here, these are counteractive load combinations. Dead loads cause negative bending moment. Wind causes positive bending moment. So the dead load counteracts the bending moment due to wind or due to earthquake. Okay. So ASD load combinations, and you see that we rely on only 60% of the dead load to counteract surface level wind or surface level earthquake. That's pretty conservative. So ASD load combinations, I don't think I left anything. Okay, this is the only thing I left out. So when a structure is located in a flood zone or in tidal surge zone, the following load combination shall be considered. In coastal zones vulnerable to tidal surges, like essentially sea waves, 1.5 F sub A, F sub A is flood load, shall be added to other loads in combinations 5 and 6. 5 and 6 are, so this is 5, this is 6. These are load combinations involving wind. This is 7, this also involves wind, but in the first one, we are talking about 5 and 6 only. So in coastal zones vulnerable to tidal surges, 1.5 F sub A shall be added to other loads in combinations 5 and 6. The earthquake effect shall be set equal to 0 in those load combinations. When we are considering tidal surge, we will also not consider simultaneously earthquake effects. In non-coastal zones, this would be flooding, etc., caused by the rivers. 0.75 F sub A shall be added to combinations 5, 6, and 7 in this case. E shall be set equal to 0. Now, this I will not get into all that much because F sub A, as I mentioned, is quite difficult to determine. Yeah, anyway, I'll talk about this a little bit before I'm through with the presentation today. It will come up in connection with strength design, right in chapter 2, and then just before the conclusion, the topic will come up again. Okay, when we do allowable stress design, can we take an increase in allowable stresses under certain circumstances? That used to be very common, but here BNBC says unless permitted elsewhere in this code, increases in allowable stresses shall not be used with the loads or load combinations given in 272. Okay, so no stress increase to go with BNBC ASD load combinations. unless permitted elsewhere in the code. Maybe masonry chapter allows it, I don't know. But generally speaking, you shall not increase allowable stresses. Okay. Strength design load combinations. Now there are factors on. So previously in ASD it was just the dead load. Now it is 1.4 times dead load when you consider dead load only. Here again, let me go to the stripped version, no F, H, or T. So 1.4 is the dead load factor when it is dead load only, but in this combination is 1.2. And anyway, the load factor on E is 1.0, as I mentioned, because earthquake effect is already at strength level. You should also note that the load factor on wind is 1.6. Okay, so I will talk about that well fairly soon. That number is kind of significant. Okay, 1.6 on the W. Okay. As I said, this is something that is repeated. I do not know why. Effects of one or more loads not acting shall be investigated. We said that at the beginning of the chapter, remember, of the section 2.7. The most unfavorable effect from both wind and earthquake loads shall be investigated where appropriate, but they need not be considered to act simultaneously. So this whole thing is a repeat and could be crossed out. Now, in the strength design load combinations, there are some exceptions. The live load factor is shown as 1.0. Okay. Here it is 1.0, here it is 1.0, here it is 1.0. That 1.0 factor on live load can be taken equal to 0.5 unless we are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load. Okay? That's 5 kilonewton per square meters. So unless, please listen carefully. So unless we are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load, the live load factor can be taken equal to 0.5 instead of 1.0. This is exception number 1. Now, not our office, ACI 318 as a committee got a significant number of inquiries about what I just talked about. Okay, so live load is allowed to be reduced as we will see. So specified live load is 50 pounds per square foot, but we are allowed to design for 40% of that, let us say. And then can we take a load factor of 0.5 on top of that? So the live load is already reduced. Can the reduced live load be further reduced by load factor of 0.5? Is that right? So ACI 318 some editions ago decided to add commentary, and I want to bring that to your attention. Load factor modification is different from live load reduction. So the 0.5 factor on the live load is different from live load reduction, which is based on loaded area and live load reduction is typically allowed in design. The live load reduction at just the nominal load L, the smaller load factor reflects. So the live load reduction accounts for the fact that if you have a large area, it is extremely unlikely that the entire area shall be subject to the full design live loads. The larger the area you are talking about, the less likely it becomes that the entire area will experience the full design live loads. So that's live load reduction. The smaller load factor reflects the reduced probability of simultaneous occurrence of maximum values of multiple transient loads. Okay, so peak live load, peak dead load, and peak of everything will not be simultaneously occurring. This is why we take 0.5 on the live load. So the live load reduction and the lower load factor on live load are account for different things. So both may be used at the same time. Absolutely nothing wrong with that. Okay, you take a 0.5 load factor on top of reduced live load. Okay, then that was the first exception, that the live load factor may be taken equal to 0.5 instead of 1.0 under most circumstances. The load factor of 1.6 on horizontal earth pressure. Here. Okay. So exception 2 says the load factor on H is 1.6 if it hurts, not if it helps. Obviously, I'm paraphrasing. The code doesn't use that language, but what it says means exactly what I said. Okay. If it hurts, then the load factor on H is 1.6. If the 1.6 helps, then the load factor on H is 1.0, not 1.6. Let me explain. If horizontal earth pressure causes bending moments in the same direction as bending moments caused by dead loads or wind, then the load factor on H is 1.6. If horizontal earth pressure causes overturning moment in the same direction as the bending moments caused by dead load or wind, then the load factor on H is 1.6. However, if horizontal earth pressure causes overturning moment in a direction opposite to that of bending moments caused by dead loads or wind, now horizontal earth pressure is counteracting the effects of the other two. Now will not take a load factor of 1.6 on H. The load factor on H will be 1.0, not 1.6. Very important. Okay, so that is exception number 2. You can read the actual language, but that's what it means. Then, for structures designed in accordance with the provisions of Chapter 6, Part 6 of this code, reinforced concrete structure, where wind load has not been reduced by directionality factor, it shall be permitted to use 1.3 in place of 1.6. It all sounds very complicated. Okay, so let me again. This is important to explain. The load factor on wind is 1.6 in the load combinations. Okay. Now, in AC 798, in the expression for velocity pressure Q, which is directly proportional to the wind pressure P, we introduced a directionality factor K sub D. An explicit directionality factor K sub D is now in the expression for velocity pressure due to wind. K sub D is called a directionality factor. It accounts for the fact that wind seldom, if ever, I shouldn't say if ever, wind is seldom in the most critical direction of the building. Wind can be in the most critical direction of the building only instantaneously. Wind direction changes from one instant to the next. The very next instant, the wind direction will have changed and it will no longer be along the most critical direction of the building. This fact is taken into account through the directionality factor K sub D, which is 0.85 for all buildings. So when the directionality factor K sub D was introduced, the wind load design wind pressure of ASCE 798 went down 15%. Very simple. We were now multiplying wind by a factor equal to 0.85. The intent of ASCE 7 was not to design for lower wind loads. Okay, so the decision was, prior to ASCE 798, the load factor on wind used to be 1.3. Now wind was lower 15%. We had multiplied wind by 0.85. ASCE 795 wind had been multiplied by a factor of 0.85. So in order to go back to the wind pressure that we were designing for under ASCE 795, the decision was, let us take the load factor 1.3 of ASCE 705 divided by the same 0.85. 1.3 divided by 0.85 gives you 1.53. Instead of rounding it down to 1.5, that was rounded up to 1.6. That was long debates and so forth, but that's what happened. Okay, so the current load factor of 1.6 on wind is the old load factor of 1.3 when wind did not include directionality, divided by the directionality factor of 1.3. So this is why exception 3 is saying where wind load has not been reduced by a directionality factor, you can go back to the old load factor of 1.3. You don't have to use 1.6. Okay? I have spent quite a bit of time. Hopefully that has been understandable. And you have the 2 slides, and so that should help you. So all 3 exceptions to the strength design load combinations are important. Now the F sub A, the flood load. So this is, you saw similar things under ASD. Now strength design, when a structure is located in a flood zone or in tidal surge zone, the following load combination shall be considered. In coastal zones vulnerable to tidal surges, 1.6 W shall be replaced by 1.6 W plus 2.0 F sub A. This is strength design, so there is a factor of 2.0. In combinations 4 and 6, I won't go back there, you can look that up. In non-coastal zones, 1.6 W shall be replaced by 0.8 wind plus 1.0 F sub A in combinations 4 and 6. Okay, so I will talk about that a little bit before I'm through, but anyway, that's where I will leave it. Okay, So now load combinations for extraordinary events where required by the applicable code standard or by the authority having jurisdiction. Strength and stability shall be checked to ensure that structures are capable of withstanding the effects of extraordinary events such as fires, explosions, and vehicular impact. So this is, how should I say, to say this is easy, to do it is not easy. If you take blast load, instance, that is a subject unto itself, but in any way the code requires that you consider load combinations for extraordinary events. Not a lot of guidance given. Okay, that brings me to load combinations for serviceability that I mentioned is in the code. So now let us get into that. Okay, so serviceability limit states like acceptable deflections, cracking, and so forth. Serviceability limit states of buildings and structures shall be checked for the load combination set forth in this section, as well as mentioned elsewhere in the code. For serviceability limit states involving, this is important, for serviceability limit states involving visually objectionable deformations, irreparable cracking, or other damage to interior finishes, and other short-term effects. So for serviceability limit states involving visually objectionable deformations, repairable cracking, or other damage to interior finishes, and other short-term effects, the emphasis is on short-term. The suggested load combinations for checking vertical deflection, this is for checking vertical deflection only, due to gravity load is just the service level dead load plus the service level live load. For serviceability limit states involving long-term effects like creep, settlement, or similar long-term or permanent effects, the suggested load combination is dead plus half of the live load. That the full live load almost never comes on the structure. So it is, so long-term effects, it is dead plus 0.5 live. This is what is being recommended in the code. The dead load effect D used in applying combinations 1 and 2 above may be that portion of dead load that occurs following attachment of non-structural elements. So you will consider the weights of the non-structural elements as well. In applying combination 2 above, dead plus half of live, to account for long-term creep effect, the immediate deflection may be multiplied by a creep factor ranging from 1.5 to 2. They are calling it a creep factor, is long-term effect factor. It could be because of reasons other than creep. Remember, in concrete, we calculate the immediate deflection, multiply that by 2 for long-term deflection, not the total. So short-term deflection, long-term deflection is equal to twice the short-term deflection. Total deflection at the end of so many years is the long-term plus the short-term deflection, which is 3 times the short-term deflection. This is similar. The long-term effect is 1.5 to 2 times the short-term effect. So in applying combination 2 above, to account for long-term creep effect, the immediate deflection may be multiplied by a creep factor ranging from 1.5 to 2. Serviceability against gravity loads, which are vertical deflections, shall be checked against the limits set forth in section such and such, as well as mentioned elsewhere in this code. And you will see the deflection limits in this table, which is part of 1.2.5, section number 1.2.5, as this was saying. Okay, so short-term load combination, dead plus live. Long-term would be dead plus half of live, and serviceability against gravity load shall be checked against the limits set forth in this table. Okay, now this table has, in addition to limits on gravity deflection due to wind as well. Okay, so that is lateral, that is coming up. Now, okay, so yeah, I'll let you read roof members, supporting plaster seating, etc., floor members, exterior walls. These are the limits on the vertical deflection caused by live loads L over 360, L over 240, etc. This is due to dead and live load. Okay, so here, okay, so when it says dead and live load, if you go by the serviceability load combination of the code, you will probably be looking at dead plus half of live. Okay, the sustained dead load plus half of live. The footnote G, some of these footnotes are important. G says deflection due to dead load shall include both instantaneous and long-term effects. So that being the case, since we are considering long-term effects of the dead load, that the L, according to what has been said in the code, can very well be 1/2 of the specified live loads. Okay, hope you are with me. Let me go further and come back for the W. So for serviceability limit state against lateral deflection of buildings and structures due to wind effect, there is no serviceability under earthquake that I'm aware of. Okay. We are concerned about strength under in seismic design, not serviceability. It is understood that there will be damage and things. For serviceability limit state against lateral deflection of buildings and structures due to wind effect, the following combination shall be used. Okay. Dead plus 0.5 live plus 0.7 wind. This 0.7 wind is interesting, and at the same time it needs to be explained, and I will try to. Due to its transient nature, wind load need not be considered in analyzing the effects of creep or other long-term actions. So this is just the short-term reflections. Okay, it is seldom that gravity loads cause lateral deflections anyway. The only time gravity loads will cause lateral deflections that will be additive to the deflections caused by wind if you have very distinct lack of symmetry in your structure. In a symmetrical structure or near symmetrical structure, dead and live loads will not cause any appreciable lateral deflections. In cases where, because you have a distinct lack of symmetry, dead and live loads may cause sideways deflection, you will take the short-term deflections. You will not worry about long-term deflections. This is what we are saying. Okay? Serviceability against wind using load combination 3 above shall be checked in accordance with limits set forth. We will go back to the table. Okay? Now, why is it 0.7 W? Wind is already so-called service level. Remember, in strength design, we multiply that by load factor of 1.6. So service level wind, why do we reduce it? That is because the service level wind of AC 705, which is in BNBC 2020, has a return period of 50 years. That is wind load that the structure is likely to experience once in 50 years. That is too high a load for a serviceability check. Serviceability check should be under more frequent wind that comes much more frequently than once in 50 years. So serviceability is typically checked under 10-year return period wind, and the 0.7 factor converts 50-year return period wind into 10-year return period wind. Okay. So you see that in the table also. There is a footnote F on the limits on wind deflections that are given in the table. And footnote F says the wind load is permitted to be taken as 0.7 times the component and cladding loads for the purpose of determining deflection limits herein. Component and cladding loads, when we go into wind design, you will see there is design of the main wind force resisting system, there is design of component and cladding. Here we are talking about, deflections of exterior walls, interior partitions, those are components. And this is why it's component and cladding load. Those are higher anyhow than the design wind loads for the main wind force resisting system. Okay. So anyway, the 0.7 factor brings the 50-year wind down to 10-year return period wind. That's the main thing I want to get across. Now here, the reference is not so much to the table, but to these drip limits that follow. 1.1562 is the next section. Anyway, let's read this. This gets pretty interesting, and I have quite a bit of problem with some of the things that are said here. Story drift. This is I don't have any problem with this. This is something you have to understand. Story drift is the horizontal displacement of one level of a building relative to the level above or below. Okay, so it is basically the deflection at the top of the story minus the deflection at the bottom of the same story. That is story drift, and we sometimes just call it drift. Deflection at the top of a story minus the deflection at the bottom of the same story, okay, caused typically by lateral loads. So story drift is the horizontal displacement of one level of a building or a structure relative to the level above or below due to the design, gravity, dead and live loads, or lateral forces, wind, earthquake. So as I said, gravity loads seldom cause lateral deflections unless there is a distinct lack of symmetry. And in that case, you will keep dead plus 0.5 on your structure as you try to calculate deflection for wind loads. Calculated story drift shall include both translational and torsional deflections and conform to the following requirements. Yeah, the translational and torsional makes a lot of sense because, all the lateral load, wind for instance, may not act. The design wind force may act uniformly on the face of your building, or in design, we also consider the possibility that half the face is loaded with full design wind loads, and the upper half of the face is not loaded at all with wind. That will give you quite a bit of torsion, and that may cause drift due to wind. So it is translational and torsional. Now, This is where I have problem, serious problem. Okay. So this is what BNBC requires: story drift delta for loads other than earthquake loads. So this will be wind. I don't know what else it would be. We typically don't have drift problems under lateral earth pressure. So story drift delta for loads other than earthquake loads shall be limited as follows. 0.005 H. H is the total height of the building. Okay, height of the building or structure for period T less than 0.7 second. So 0.5% of H total height for period less than 0.7 of a second, or the interstory drift less than or equal to 0.4% of the total height for the more flexible buildings, period exceeding 0.7 of a second. Now, I do not understand at all, and I have never seen this in my life, story drift limit related to the entire building height. To me, does not make any sense. When we set limits on drift, story drift, we relate it to story height. As you will see in seismic design, it is so many percent of the story height. That makes all the sense in the world. To relate to restrict the interstory drift to a percentage of the total height of the building, to me does not make any sense. And the distinction between the rigid building and the more flexible building based on the period that we use in seismic design, that does not make a lot of sense either. So I have very serious problem with 1561. In due respect, I don't understand it. I don't think it makes any sense. The drift limits set out in A above that I commented on may be exceeded where it can be demonstrated that greater drift can be tolerated by both structural and non-structural elements without affecting life safety. That is a good provision, but that demonstration is not easy. For earthquake loads, the story drift delta shall be limited in accordance with that I will discuss in great length when we do earthquake design in a couple of days. Okay. So that brings me to the various loads. We are now going beyond the load combinations. It's not quite 9:30, but this is a good point for a break. So let's come back at 28 after the hour, 5 minutes. Let's take a short break of 5 minutes. 28 after the hour, I'll start again. Okay, thank you. Okay, the 5 minutes I think are up. So we'll start again with dead loads. Of the major loads given in chapter 2, wind and earthquakes we will deal with separately, so it is only the rest of it that we will discuss today. Dead loads, by definition, dead load is the vertical load due to the weight of permanent structural and non-structural components, permanent, and attachments of a building, such as walls, floors, ceilings, permanent partitions, and fixed service equipment, etc. You know this. Okay. Dead load for a structural member shall be assessed based on the forces due to weight of the member itself, weight of all materials of construction incorporated into the building to be supported permanently by the member. And I find this written in an interesting way. So what I think is being said is the weight of the member itself, and then the second item is, whatever else. If like a beam supports a part of a slab, so item 1 says weight of the beam itself, item 2 says the weight of the part of the slab that is supported by the beam. Then weight of permanent partitions as opposed to partitions that are movable, as you see in office buildings more and more. Weight of fixed service equipment. And the last item how should I say, I find kind of surprising, net effect of pre-stressing. I have never, in calculating dead load, I have never tried to calculate the net effect of pre-stressing of a pre-stressed member. I don't know anyone who does. Pre-stressing does act as negative dead load much of the time, if not all the time. But that is accounted for in the design of the member. I do not know that we include it in dead load calculations. So I do not quite know what the writers had in mind. In estimating dead loads, the actual weights of materials and construction shall be used, provided that in the absence of definite information, the weights given in tables 621, 622 shall be assumed for the purposes of design. So you are, I think, very lucky that you have those tables in the code. Unit weight of basic materials, weight of construction materials. So those are given to you. The tables are pretty extensive, and those are not commonly given in codes, let me say. So you have major help from those two tables in calculating dead loads. Weight of permanent partitions. When partition walls are indicated on the plans, their weight shall be considered as dead load acting as concentrated line loads in their actual positions on the floor. That is totally understandable, and I don't know that I need to explain any of that. The loads due to anticipated partition walls which are not indicated on the plans, that is the important part, shall be treated as live loads and determined in accordance with section 236. We will go there. But the point is that the significant point is that permanent partitions are dead loads. The load factor is lower. Movable partitions are live loads, and the load factor on that is higher. A live load factor is what you apply to the weight of movable partitions. Fixed service equipment. Weights of fixed service equipment and other permanent machinery, such as electrical feeders, other machinery, etc. So any fixed equipment, the weight, including operating weight of water or whatever is inside, all of that is dead load, and the code is very specific about that. Then there are these additional loads in evaluating the final dead loads on a structure. This again I find a little bit problematic. It is in the BNBC. I think the thought is admirable, but I do not believe that this is practice or common practice. In evaluating the final dead loads on a structural member for design purposes, allowances shall be made for additional loads resulting from difference between the prescribed and the actual weights of the members and construction materials. So we are being asked to make allowances for differences between the prescribed and the actual weights of members and construction materials. So you have taken concrete weight at 150 pounds per cubic feet. What if it is 153 pounds per cubic feet? Again, this is very uncommon to make allowance for that in dead load calculation. Inclusion of future installations, changes in occupancy. So again, the only thing that I know is commonly done is designers quite often would design for significantly higher live loads than prescribed in the table in the code. and that accounts for possible changes in occupancy in the future. Your specified live load is 50 pounds per square foot. You may want to design for 80 pounds per square foot because that gives you some flexibility in the future. But changing your design dead load to account for future changes in occupancy, this is very uncommon. Inclusion of structural and non-structural members not covered. So all of that, the entire section on additional loads, as I said, the thought makes sense, but I do not believe this is common practice. And if you ask me, I wouldn't know what to consider, how much to consider. The net effect of pre-stressing is a bit of a surprise, and that provision also is not a surprise, but when you put that stuff in the code, it's a little bit of a problem, because then that gives the authority having jurisdiction the opportunity to be unreasonable, and the engineer has to argue. Anyway, so live load is the load. Live load is the I want to emphasize this. Live load is the reason we put up a structure to carry that. The sole reason why we put up a building is that we want to impose live loads on that building. Live loads are the loads that we impose on a structure as a result of the activities we carry on in the structure. We dance on the floors, that applies live loads. We sleep on the floors, that applies live loads. We take classes on the floors, that applies live loads. Okay, and that is the reason we are constructing our structure. Everything else, absolutely everything else, all the other loads are parasitic loads. Dead loads is the first one. In order to impose live loads on our structure, we have to design to carry the weight of the structure, which is much more than the live loads, but we have no choice. Wind is a parasitic load that's always present. We have to do something about it. Otherwise our structure will be blown away. So, so that perspective is important. Live load is the reason why we erect our structure. Live load is the load. Superimposed, why it says super, I don't know, I would have said imposed by the use or occupancy of the building, not including the environmental loads such as wind load, rain load, earthquake load, dead load. So all those, dead load is not an environmental load. Why they wrote it here, I don't know. But anyway, live loads are exclusive of those. Now, minimum floor live loads, I think I'll skip the writing here. So the way everybody designs is there is a table in the code that gives you minimum uniformly distributed live loads. And then there are also concentrated live loads given in the same table. You design for one or the other, whichever is the more severe. It is not that you design for the uniformly distributed plus the concentrated. No, it is never that. Okay, it is one or the other. So maybe it may not be a bad idea to read. The minimum floor live load shall be the greatest actual imposed loads resulting from the intended use or occupancy of the floor. Okay, so theoretically, whatever will be imposed is what you design for, but you shall not go below what is given in the table. See, in reality, everybody designs for the tabulated values. Except in unusual circumstances, one wouldn't try to figure out the live load that will be applied on your structure. Okay. So specified in 234 or the concentrated load specified, whichever produces the most critical effect. Okay. The one or the other, not both, whichever is the more critical. The live load shall be assumed to act vertically upon the area projected on a horizontal plane. This is also important. Okay. So this is vertically on the horizontal projection. That's how live loads are always applied. Uniformly distributed loads are in the table 623. Concentrated loads are also in the same table 6.2.3. Here maybe I should point this out, unless otherwise specified, the concentrated load shall be applied over an area of 300 millimeters by 300 millimeters. Okay, that is important, and shall be located so as to produce the maximum stress conditions in the structural members. So both of those things are important. The concentrated load shall be applied over an area of 300 by 300 millimeter, shall be located so as to produce the maximum stress conditions in the structural members. And that location may or may not be obvious. You may have to try a number of locations. The partition walls, the movable walls that I was talking about, when partitions not indicated on the plans are anticipated to be placed on the floors, their weight shall be included as an additional live load. This is a live load acting as concentrated line loads. This again, I is not what I typically see. What people do is this minimum. So such uniform live load per square meter shall be at least 33% of the weight per meter run of partitions, not even that, subject to a minimum. This minimum value is what everybody uses, okay, for movable partition loads, 1.2 kilonewton per square meter. This is the BNBC 2020 minimum movable partition load. That comes to 25 pounds per square foot in our units. IBC, we consider 15 pounds per square foot. I did want you to understand that. 25 pounds per movable partitions is an awful lot. It will be greeted with so much protest in this country that I can't even tell you. So I do not know why it is that high. Maybe the movable partitions are made of different material. I do not know, but it's a surprisingly high number. But anyway, that's the minimum, 25 pounds per square foot in BNBC. I don't think I have made any mistake. It's very clearly 1.2 kilonewton per square meters. One is about 20. Okay, more than one occupancy. When an area of a floor is intended for two or more occupancies at different times. Okay? Two or more occupancies at different times. During the day, it's one thing. During the night, it's another thing. Okay? During the night, you sleep. During the day, maybe, people come in and you hold classes. So whatever, the value to be used from the table shall be the greatest value for any of the occupancies concerned. That makes sense. Minimum roof live loads. So floor live load is L, roof live load is L sub R. Roof live loads shall be assumed to act vertically over the area projected by the roof or any portion of it upon a horizontal plane like all live loads, and shall be determined as specified in table 624. So the table that gives you floor live loads also gives you roof live loads. Same. I how do I want to say it? So the table that gives you pro-live loads that we have been talking about is table 6.2.3. That table has an entry for roof live loads. So roof live loads are in the same table as pro-live loads, 6.2.3. But the entry for roof live loads in table 6.2.3 makes reference to another table, 6.2.4. So I haven't anyway. So roof live loads comes from let us say 6.2.3 is the main table that you will go to, and you will go to 6.2.4 when table 6.2.3 sends you there. That's the best way to say it. Okay. Loads not specified, live loads not specified for uses or occupancies shall be determined from loads resulting from weight of. You can read this. I have nothing to add. That will help you. Partial loading or other loading arrangements. These things are now. You remember. Let's go there. Here, where uniformly distributed live loads are used in the design of continuous members and their supports, consideration shall be given to full dead loads on all spans in combination with full live loads on adjacent spans. That will give you the highest support moment, and on alternate spans. Whichever produces a more unfavorable effect. So this so-called pattern live load, it is a requirement of the code, but more and more we don't spend time doing that. You know, it takes, it's labor intensive, and the benefits are kind of limited. So more and more these pattern live loads and things are just not done in design offices. I do not know that is violation of the code. It is just like moment redistribution is simply not done anymore. So I'm not telling you don't do it, but all I'm telling you is that the current circumstances typically don't allow you to spend that kind of time. Okay, so live loads on miscellaneous structures and components such as handrails and supporting members, those are important. Those are given in a table in the BNBC 6.2.5 miscellaneous live loads. Very important table, fairly extensive table that I have chosen not to reproduce. This is something I'm very glad BNBC has. This is very helpful. The live load specified in whatever shall be assumed to include allowances for impacts arising from normal uses only. So the live loads that we use that are in the table include allowances for impacts arising for normal uses only. However, forces imposed by unusual vibrations and impacts resulting from the operation of installed machinery and equipment shall be determined separately and treated as additional live loads. Live loads due to vibration. Anyway, you can read all of that. The good thing I think is BNBC has given you this table. So additional load. So this is equipment or machinery that you are dealing with in your building. Additional load due to impact as percentage of static load, including self-weight. So for lifts, hoists, and related operating machinery, you will increase the dead load that is tabulated by 100%. Okay. Light machinery, you will increase by 20%. So minimum live loads on supports and connections of equipment due to impact. So any area supporting light machinery, you will increase the live load 20% because of impact. So that table definitely is very, very helpful. In the US, you are not given that kind of a table. Okay, the very important topic of live load reduction. It used to be in the old days based on tributary area, which we all understand. Anyway, you'll see pictures. And then in AC 795, they decided to base live load reduction on the so-called influence area. And this again, I'll explain, tributary versus influence area. This was the formula in AC 795. Your document is AC 705. BNBC 2020 is based on AC 705. Okay. So L sub 0 is the unreduced live load. L is the reduced live load. A sub I is the influence area. Reduced design live load shall be not less than 50% of L sub 0 for members supporting one floor. Not less than, so members supporting one floor will be slabs and beams. Not less than 40% of L sub 0 for members supporting two or more floors. Those would be columns and walls. Okay. Now, influence area is the entire area that influences the load on that column. This is not tributary area. Tributary area is the area that contributes load to the column, directly supported by the column. Influence area is the area that influences the load on that column. So for that exterior column, the influence area is the area of those two panels. For the corner column, it is the area of one panel. For the interior column, is the area of the four panels. For a beam, interior beam, those two panels. For the exterior beam, that panel. For that beam, it is that panel. Okay. So influence area. AC 795 introduced the formula that I showed you and also included this picture in the commentary to explain what the influence area is. But there was quite a bit of confusion about what influence area is when there are overhangs. People didn't understand what is the influence area. So in the next edition of AC 7 dated 98, which hasn't changed since, so this is what you have in BNBC. The formula didn't change, but the influence area was expressed as a constant times the tributary area, which everybody understood. Okay. So K sub L, so influence area now was this K sub LL times the influence times the tributary area. L shall not be less than 50% of L sub 0 for members supporting one floor as before, nor less than 40% of L sub 0 for members supporting two or more floors. Okay. And AC 798 gave you this very nice picture of tributary area and influence area superimposed on top of each other. Okay. So for this column, this is the tributary area, this is the influence area. This overhanging beam, this is the tributary area, this is the influence area. And so on and so forth for everything. For this column, this is the tributary area, this is the influence area. So this is a very, very nice picture. Essentially remove the confusion. The influence area now was this K sub LL times the influence times the tributary area, and K sub LL is given in this table. Okay. Interior columns is 4, exterior columns without cantilever slabs is 4, and so on and so forth. Okay. So Limitations on live load reduction. Live loads that exceed 100 pounds per square foot cannot be reduced. 4.8 kilonewton per square meter. Exception to that, live loads for members supporting 2 or more floors may be reduced by 20%. So columns and wall loads up to 20%. Okay. So heavy live loads cannot be reduced, except live loads for members supporting 2 or more floors may be reduced by 20%. Passenger car garages, same thing. Live loads shall not be reduced, but the exception says live loads for members supporting 2 or more floors may be reduced by up to 20%. Special occupancies. Live loads of 100 pounds per square foot or less shall not be reduced in public assembly occupancies. So more than 100 pounds per square foot you cannot reduce anyway. If it is public assembly occupancy, then even less than 100 pounds per square foot you cannot reduce. And there shall be no reduction of live loads for cyclone shelters. This is in BNBC. So live loads of 100 pounds per square foot or less shall not be reduced in public assembly occupancies, and for cyclone shelters, no reduction of live load. The tributary area A sub T for one-way slabs shall not exceed an area defined by the slab span multiplied by 1.5 times the slab span. So that is the largest tributary area that you can get for a one-way slab. The span of the slab multiplied by 1.5 times the span of the slab. So there is, in effect, an effective width that is 1.5 times the span of the slab. Okay, the minimum uniformly distributed load. So roof live load, L sub 0 is the unreduced value. As I said previously, it is given in table 623, 624. You go to 623 first, and if it sends you to 624, you go there. This is table 624. I find it pretty interesting. So flat roof, 1 kilonewton per square meter. This is 20 pounds per square foot. Yeah. And then pitched or sloped roof, slope between 1/3 and 1, it goes down to 0.8 kilonewton. Anyway, as the slope increases, the load goes down. So there is a reduction for roof slope in table 6.2.4. Same thing for arched or domed roofs. And then there is this roof live load reduction factor taken from AC 705, which says the reduced roof live load is the unreduced roof live load times a reduction factor for area and a second reduction factor for roof slope. Okay. And the roof live load shall never be reduced more than 40%. So the reduction factor based on area depends on tributary area. That's understandable. The reduction for slope, the R2 part, depends on the slope of the roof. This F is for a pitched roof. F is 0.12 times the slope, with slope expressed in percentage points, and for an arch or dome, F is rise to span ratio multiplied by, anyway, details aside, there is a reduction for roof slope right here. Now, I am absolutely convinced that you should not take this reduction for slope and also that reduction for slope. If you are going to use the R2 factor, then stick with 1 kilonewton per square meter as your roof live load, then take the reduction that is given by the formula, or you stick to the table and forget about R sub 2 in the formula. I'm absolutely convinced that you cannot take two reductions for the same roof slope. Okay, so that part of BNBC is a bit confusing. They do not tell you that. Okay, special purpose roofs. Roofs that have an occupancy function, such as roof gardens, assembly purposes. Many times people assemble on roofs, you know that quite well. And other special purposes are permitted to have their uniformly distributed live load reduced in a so then you basically design for floor live load and you take floor live load reduction. If your roof is going to be used for assembly, you design for assembly live load and then you reduce it. The assembly live loads cannot be reduced, as you saw. Okay, so anyway, so then the live load on that area of the roof shall be treated as floor live load. That's pretty much what we are saying. Okay, so this is a live load reduction example that you may find to be useful. Plan dimensions as shown. We will go there. Story height is 4 meters. Live load 2.4 kilonewton per square meter on the floors, 1 kilonewton per square meters on the roof. Dead load on the floors 5.8 kilonewton per square meter, roof 4.3 kilonewton per square meter. I don't know that we'll need the dead load. Okay, the plan shows the spans in one direction 7 meters, in the other direction 8 meters. We have shear walls on the two faces, otherwise these are columns. This is the elevation, the 4 meter height. We are calling this level 1, this is level 2, this is the roof. Roof is treated separately. Okay. So I think we have calculated live load reduction for the corner column and the shear wall. Those are the two elements for which we have done our calculations. So the tributary area for the column, for the corner column, would be half of 7 meters, that's 3.5, and half of 8 meters, that's 4. 4 times 3.5 would be 14 square meters. So the upper level is 14 square meter, lower level columns accumulate the tributary areas. So we are looking at 28 square meters. The unreduced live load was given in the problem statement 2.4 kilonewton per square meters. K sub LL, if you go back to, we may have to go a long way back, but it may be worth it. Should have copied it again. K sub LL for exterior columns without cantilever slabs is 4. And the shear wall, when we get there, will be under all other members not identified above. Identified above are exterior columns without, interior columns, exterior columns without cantilever slabs, edge columns with cantilever slabs, corner columns. Okay, these are all columns, and then everything else you have K sub LL of 1. So for the corner column, you have K sub LL of 4. So the influence area will be 4 times the tributary area. 4 times 14 is 56, 4 times 28, 112. So from the live load reduction formula, the reduction comes out to 13.9% based on that area. and 31.8% based on that area. Maximum reduction we can take is 50. We did not hit that. Here, the maximum reduction we can take is 60. Remember, 2 or more floors. We cannot go below 40% of unreduced live load, means we cannot take more than 60% reduction. So actual reduction is 13.9% here, 31.8% here. This number is the 2.4 multiplied by 1 minus 13.9%. If it is 13.9% reduction, then 86.1% of the unreduced load is the reduced load. Okay, so this is the 86.1% of 2.4, 2.06. Okay. So these are simple numbers, but I can attest to the fact that there is a lot of confusion. So please, we did not take the roof load as contributing to the column live load. That is one thing I need to stress. In the old days, long after I started off, there was no distinction between roof and floor. This is, to me, this is relatively new, although this probably happened, I don't know, 25 years ago. Anyhow, so now the roof is treated totally separately. You deal only with the floors. Anyhow, I think you will find the simple example to be of benefit. For the shear wall, if you go back to the figure which I owned, the tributary area comes to 112 square meters. So the first level would be 224, 2 times that. The unreduced live load is the same as before. K sub LL, as I pointed out, is now 1, not 4 anymore. This is a shear wall. It falls under all other things. So the influence area is the same as tributary area. Based on this, we get a 31.8% reduction, which being less than 50 is what we get. And based on the larger tributary area, we get a 44.5% reduction, which being less than 60 is what we actually get. So the reduced live loads are 1.64 rather than 2.4. This is not PSF. This is kilonewton per square meter. Did I have PSF on the other one? Yeah, I forgot to change that. Okay, so sorry about that mistake. This is kilonewton per square meters. Okay, so 1.64 and 1.33. A little bit of a question and answer. Can partition loads, meaning movable partition loads, be reduced since they are live loads? The answer is nowhere does BNBC 2020 say explicitly that partition loads cannot be reduced. However, it is believed that it cannot be reduced because it is not listed in that table 6.2.3. We really believe that it is the tabulated values that can be reduced. No. So movable partition load, do not take a reduction, would be my advice. Okay, the miscellaneous loads, rain loads, loads due to, you have seen this this list, and not all of those things are discussed in BNBC anyway. Rain loads, actually most of these items in this list to me are a bit of a question mark. I do not fully understand what is being required or what is being said, and I'm being totally frank with you. You may have to figure it out on your own, or maybe you know it already. I don't, at least I don't know. To me, it's not unambiguous or clear. Okay, so let's take rain loads for instance. rain loads shall be determined in accordance with the following provisions. So following provision, the first thing it says blocked drains. Each portion of a roof shall be designed to sustain the load from rainwater, the load from all rainwater that could be accumulated on it if the primary drainage system for that portion is undersized or blocked. I'll read again. Each portion of a roof shall be designed to sustain the load from all rainwater that could be accumulated on it if the primary drainage system for that portion is undersized or blocked. Ponding instability shall be considered in this situation. Ponding instability is the accumulated water will cause deflection. So the bending moment caused by that deflection will cause additional deflection, and all of that may eventually lead to failure of the roof. Ponding instability, that is a problem dealt with in ASC 7, little more than in BNBC. Now my question is, does that tell you, let us say we have a roof with a 3-foot parapet, okay, 1 meter tall parapet. So when the primary drain or drains are blocked, do we design it for 3 feet of standing water? Is that what it is telling me? I do not know. This is just a question. The load from all rainwater that could be accumulated on it if the primary drainage system is blocked. What if instead of a 3-foot parapet, we have a 6-foot parapet? Do we then design for 6 feet of water? Doesn't make a lot of sense to me. So how do we figure this? The load from all rainwater that could be accumulated on it. I do not know. Okay. Controlled drainage. Roofs equipped with controlled drainage provisions shall be designed to sustain all rainwater loads on them to the elevation of the secondary drainage system plus 1/4 kilonewton per square meter, that's 5 pounds per square foot. So shall be designed to sustain all rainwater loads on them to the elevation of the secondary drainage system plus 5 pounds per square foot. Ponding instability. This is much more understandable because that is a defined level. So loads on them to the elevation of the secondary drainage system plus 5 pounds per square foot. Now, so a secondary drain could be as shown in the picture. Okay, primary drain would probably not have this dam kind of thing. Okay, so a primary drain would be just that on the floor of the roof. A secondary drain would look something like here. Okay, so the language tells you that. Let's read that language. Roofs equipped with controlled drainage provisions shall be designed to sustain all rainwater loads on them to the elevation of the secondary drainage system. So to me, that would be all the water up to this level plus 5 pounds per square foot. That to me is something I understand. I do not have any problem. Okay. But I did want to throw in that to my mind, this was a very unclear provision also in ASC 716. for the longest time, I had a lot of trouble figuring out the design rain load until clarity came in AC 716. And I have included some stuff out of AC 716 that I have no time or intention to go into. But I did want to point out that this is a pretty complex subject. What AC 716 tells you to do makes use of extensive tables given in the commentary to AC 716. You need those tables, and you also need the design rainfall intensity. And the design rainfall intensity depends on the duration of the rain and the return period on the rain, like 50-year return period, 15-minute duration rain. Then you can find the design rain load intensity. So the usual design rain load uses 60-minute duration of a 100-year return period rainfall event for the design of primary drainage system, 15-minute duration of a 100-year return period rainfall event for secondary drainage system. And those numbers can be found from a website that is maintained by the National Weather Service, the National Oceanic and Atmospheric Administration, NOAA. So all I'm trying to say is that the subject is significantly more complex. If you look at AC 716, but if BNBC simply means that you take the weight of water up to that level and then add 5 pounds per square foot, and that's your rain load. That's fine. I won't quarrel with it, but make sure that that's what it is saying. What BNBC is saying for rock drains where there is no controlled drainage, this is something I frankly do not understand. How you will figure that, I have no idea. Okay, so that's where I will leave rain loads. Okay, loads due to flood and surge. This is another in my opinion, a kind of a problem area. Okay, let's read what BNBC has to say. So for structures sited at inland areas subject to flood, loads due to flood shall be determined considering hydrostatic effects, which shall be calculated based on the flood elevation of 50-year return period. Okay, that's an understandable sense. So for structures sited at inland areas subject to flood, not coastal area, inland area subject to flood, loads due to flood shall be determined considering hydrostatic effects only, which shall be calculated based on the flood elevation of 50-year return period. Now, where that statistic is available, I do not quite know, but that's what BNBC is saying. For riverside structures such as under exposure C, that is wind exposure C, which we'll discuss tomorrow, hydrodynamic forces, not just hydrostatic, arising due to approaching wind-generated waves shall also be determined in addition to the hydrostatic load on them. In this case, the amplitude of such wind-induced water waves shall be obtained from site-specific data. Okay, so what you are being asked to do is, in my opinion, not easy to do, and you will need the site-specific data. Where that will come from, I am not sure. So this is for structures sited at inland areas subject to flood. Then there are coastal areas that are marked on this map. That's part of BNBC. High risk areas are the bright red, and risk area are the pink. Okay, so these are very clearly just the coastal areas. Now, coastal areas is where you were asked to add the F sub A to the load combinations, remember? And I may have intended to, I may have dropped one section here, 2632, I'm not sure. In any case, in coastal areas, you are supposed to add the flood load part, the F sub A. Yeah, let me check one thing quickly. Yeah, I did as I suspected. I will add this slide in the posted version. So the next section reads, and this I meant to include, coastal areas of Bangladesh has been delineated as risk area and high risk area based on the possible extent of the inland intrusion of the cyclone storm surge as shown in the map that I showed you. To be classified as coastal risk area, the principal source of flooding must be sea tides, storm surge, and not riverine flood. Okay, it has to come from the ocean, not the river. The RA risk area extends from the coastline to an inland limit up to which surge water can reach. So risk area is all the area that can be covered by surge water. The high risk area includes a strip of land within risk area. It extends from the coastline up to the limit where the depth of storm surge inundation may exceed 1 meter. So where the inundation may exceed 1 meter is where you have high risk area. Entire area of the offshore islands except the Moheshkhali area is included in high risk area. A part of Moheshkhali is covered by hills and therefore free from inundation. However, the western and northern parts of Moheshkhali are low elevation and risk inundation. For structures sited in coastal areas, the hydrostatic and hydrodynamic loads shall be determined. And then there is quite a bit given in the code itself. So 2632, I will add a slide and it will be posted. So the high risk areas and the risk areas are clearly marked. And as I said, BNBC has told you quite a bit now whether you can determine flood load F sub A from what is given there. I have not invested the time to figure out. And it talks only about hydrostatic and hydrodynamic loads. In the US, the standard that gives you, supposed to give you flood loads is ASCE 24, the standard that you see before you, flood resistant design and construction. The 2014 edition is the second edition of the standard. The first edition was about 10 years earlier, 2004-05 kind of time frame. This was developed with FEMA money, and anyway, this standard talks about hydrostatic loads, hydrodynamic loads, debris impact, which is a major thing in when there is storm surge, and also scour of the foundation, which is another huge problem. The point that I'm trying to make is, having gone through ASCE 24 carefully, I had no clue how to figure out F sub A, the flood load that you use in design. And our company publishes the so-called code masters, and we have one on flood loads that I had done by the chair of the flood committee of ASC 7. And here he explains how to calculate F sub A. So it's not that I don't, it's not easily available information. So the point that I'm trying to make once again is, if you are in a coastal area, you will have to figure out the F sub A for design purposes. BNBC tells you quite a bit about calculating hydrostatic and hydrodynamic forces. Whether that enables you to calculate F sub A relatively easily, I haven't invested the time to tell you. So please figure it out for yourself if you are designing structures in a coastal area. Okay, temperature effects. Now here, the code in section 264 actually talking about temperature effects, not the restrained volume change that I was talking about in the beginning. Okay. So, and what it says is kind of interesting. So let us invest the time to read this. Temperature effects, if significant, shall be considered in the design of structures or components thereof in accordance with the provisions of this section. In determining the temperature effects on a structure, the following provision shall be considered. The temperatures indicated shall be the air temperature in the shade. The range of the variation in temperature for a building site shall be taken into consideration. Okay? Taken into consideration, where you will get it is up to you. The range of variation of temperature. Effects of the variation of temperature within the material of a structural element shall be accounted for by one of the following methods. Relieve the stresses by providing adequate numbers of expansion and contraction joints. This, I think, is very bad advice, because the joints are a headache to maintain through the lifetime of the structure. So we avoid joints to the extent possible. Yeah, they are a possible solution, but they are not a good solution. The second is, design the structural element to sustain additional stresses due to temperature effects. So the temperature effect, the structural member wants to shorten or lengthen, or both, wants to go up and down, and I remember a parking structure. It was in Phoenix or some such place, and there were enormous problems with the roof, because in the sun it would want to go up, and in the dark at night the slab would come down because of the temperature variations, which are extreme in Phoenix. You go to 100 and, well, Fahrenheit degrees don't mean much to you. Anyway, extreme temperature differential from day to night. Anyhow, so design the structural element to sustain additional stresses due to temperature effects. When the second method is considered, that you will calculate essentially the loads due to temperature differential. When the second method is considered to be applicable, the structural analysis shall take into account the following: the variation in temperature within the material of the structural element, exposure condition of the element, and the rate at which the material absorb or radiate heat, the warping of any other distortion caused due to temperature changes, etc. So this is easy to say. All of this is very difficult to do. The effects of temperature on a structure, to analyze for that, is far from simple. Pre-stressed precast people who design in precast have to deal with restrained volume changes all the time. So they have practical solutions. Something popped up. Okay. And my advice would be, if you have to deal with this temperature effects, really deal with them. Look at the PCI design handbook, and it may give you ideas. This kind of analysis is very difficult, and I don't even have a good reference for you. I'm sorry to be that negative, but that's the situation. This is my experience. It's very tough to satisfactorily figure out the effects of temperature by analytical means. When it can be demonstrated by established principle of mechanics or by any other means that neglecting some or all effects of temperature does not affect the safety and serviceability of the structure, the temperature effect can be considered insignificant, need not be considered in design. When it can be demonstrated by established principle, I don't exactly know how you will demonstrate that. Okay, I think the final load is I think this is the last one that we will talk about. Soil and hydrostatic pressure. So for structures or portions thereof lying below ground level, loads due to soil and hydrostatic pressure shall be determined in accordance with the provisions of this section and applied in addition to all other applicable loads. So first is pressure on basement wall. So this is horizontal earth pressure, as I've been talking about. This is the H. Okay? If there is no earth, it is just liquid, it would be F. Now the how do you call it, the next section, uplift or uplift, yeah. So that would the uplift of the floor due to the water underneath, that would also be typically treated as H rather than F, although that is a discussion in itself that we don't have time or luxury for today. So pressure on basement wall. In the design of basement walls and similar vertical or nearly vertical structures below grade, provision shall be made for the lateral pressure of adjacent soil. Allowance shall be made for possible surcharge due to fixed or moving loads. So you store a lot of material on the site. That itself is like added head of water, and that needs to be considered. So allowance shall be made for possible surcharge due to fixed or moving loads. When a portion or the whole of the adjacent soil is below the surrounding water table, computation shall be based on the submerged unit weight of soil plus full hydrostatic pressure. Now the water will apply pressure, and the if it is sand, the sand will apply pressure. So fully submerged under the water table. Uplift on floors. In the design of basement floors and similar horizontal or nearly horizontal construction below grade, the upward pressure of water, if any, shall be taken as the full hydrostatic pressure applied over the entire area. The hydrostatic head shall be measured from the underside of the construction. I think this is understandable upon reading. The only question mark is whether it is H or F, and if I read it correctly, BNBC pretty much tell you that this is H. It's a question of which load factor you apply. Okay. Now I again will not take you through this, but in the IBC, this topic is treated. IBC, I just want to show you, has this table that you can use. The soil classification comes from this ASTM D2487. Okay, well graded, clean gravel sand mix. This is GW. To CL is inorganic clays of low to medium plasticity. Depending upon what kind of soil you have the lateral pressure that you can use in design. You don't have to, but you are allowed to use those values. Now, I want to mention to you. Sure. So I think this is probably necessary to read to understand IBC. Foundation walls and retaining walls shall be designed to resist lateral soil loads from adjacent soil. Soil loads specified in the table shall be used as the minimum design lateral soil loads unless determined otherwise by. So what is recommended? You get the values from a geotechnical engineer. In the absence of that, you can use the table. So unless determined otherwise by geotechnical investigation in accordance with section such and such. Foundation walls and other walls in which, so please follow this closely, foundation walls and other walls in which horizontal movement is restrained at the top shall be designed for at-rest pressure, as it is called. Okay, so foundation walls and other walls in which horizontal movement is restricted at the top shall be designed for at-rest pressure. Retaining walls free to move and rotate at the top shall be permitted to be designed for active pressure. So there is at-rest pressure and active pressure. So at-rest pressure is here, the active pressure is here. Okay, the active values are lower, the at-rest values are higher. And this at-rest versus active is defined here, as I read. Foundation walls and other walls in which horizontal movement is restricted at the top shall be designed for at-rest pressure. Retaining walls free to move and rotate at the top shall be permitted to be designed for the lower active pressures. Lateral pressure from surcharge loads shall be added to the lateral soil load, as BNBC says. Lateral pressure shall be increased if expansive soils are present. Foundation wall shall be designed to support the weight of the full hydrostatic pressure of undrained backfill unless a drainage system. Okay, those details I will not go into. The only other thing is, until the 2021 IBC, there was no mention of this uplift in the IBC. But now there is language, and this language almost mirrors what you have in BNBC. Okay, almost identical language as far as the uplift is concerned. Okay, erection and construction loads. All loads required to be sustained by a structure or any portion thereof due to placing or storage of construction materials and erection equipment, including those due to operation of such equipment, shall be considered as erection loads. Provision shall be made in design to account for all stresses due to such loads. This I personally do not quite understand. Let me, I know it's kind of late. We need to go to question and answer. So this is the way I see it. First of all, it is means and methods. Those are not treated in building codes, at least in the US. Secondly, this is what kind of bothers me. So take a multi-story concrete building, which is the majority of construction in Bangladesh. Now, it's not just that concrete building. Any building will see the highest loads it will ever see during its service life, during the period of construction. Okay, that's the highest loading, because you store stuff on the floors, workers are walking around, and also the concrete is green. It hasn't quite gained the full strength that it is going to gain in time. So initially, we obviously, concrete is short. It has to be temporarily supported before the concrete hardens. So we have formwork supported by shoring. There is a lot of pressure from the contractor to remove the formwork as soon as possible for reuse. So while the concrete is still green, I don't know, 4 or 5 days after construction, you will remove the shores, remove the formwork, but then we invariably reshore. We now install the shores directly supporting the concrete slab. There is no formwork in the picture. Okay? And those reshores are kept in place should be kept in place for quite some time in order for the slabs not to deflect too much under these construction loads, the stored material with people walking around, etc. So that's how construction loads are. Bulk of it is treated. We design the structure for service loads, assuming that it has gained full strength, 28-day strength, and so forth. And the construction loads are under means and methods, and we take care of them by temporarily supporting the structure when it needs to be supported. So when BNBC says all loads required to be sustained by a structure due to placing or storage of construction materials and erection equipment, including those due to operation of such equipment, shall be considered erection loads. Yeah, erection loads, that's fine. But provision shall be made in design to account for all stresses due to such loads. That part I frankly do not understand. I do not know what I'm supposed to do. So this is probably the third time I told you that today. But that's my honest reaction to what is in BNBC, and maybe we should collectively question those things and figure out. Okay, that's yeah. I didn't expect this to take so much time, but here we are, 11:15. But I'm open to questions, and we'll handle them the same way. Bodhi will read them to me, and if I can answer, I will answer.
Thank you, Dr. Ghosh. And we don't have much time. Actually, we have just 20 minutes. So I'll go over the questions one by one. So can you suggest some books on load calculation examples as per AC 705?
Load calculation examples, yeah. David Vanilla has a whole.
Yeah.
Maybe we can put the exact reference on the PRP. Yeah. There are books actually, not just one. Very good ones that show all the loads, including the very difficult rain loads and so forth. Yeah, we'll give you references.
Okay. So BNBC 2020 section 2.6.4 discusses temperature change or variation to be considered in structural design. However, what is the temperature load or temperature change or variation that should be considered is not mentioned in BNBC 2020. Please advise.
I was saying the same thing. I do not have any advice. It has to be case by case. I do not know. I kind of vaguely remember, I think it was somebody from Dubai that hired us. You may not remember, but you may not have been involved. And we tried to figure it out, and it was a major pain. And I cannot advise, except that it has to be taken case by case. The restraints are different. The what is happening is different. So as I said, it's a complex problem, has to be treated case by case, and beyond that, I do not have any advice. And I myself was saying that BNBC doesn't help you.
Okay. So one question is, when concentric load is mentioned in load tables in BNBC, when should it be considered?
Concentric load or concentrated load?
Concentrated load, I guess.
Yeah, concentrated load. Yeah. The requirement is that you are supposed to always consider it. You need to consider uniformly distributed. You also need to consider concentrated loads. Concentrated loads are more complex because you have to place it where it causes the worst effects. And then you are supposed to go with the worst of the two, whether the uniform loads gives you the worst situation or the concentrated loads gives you the worst situation. Now, beyond that, there is just experience that guides you. Like if you are designing sleeping areas, I have never seen the concentrated loads govern or people considering them. On the other hand, in parking garages, the concentrated loads do need to be considered, and in some cases they turn out to be pretty important. So my overall impression is that most of the time we design for the uniform loads, although there are some applications where we know the concentrated loads to be potentially more critical, and then we consider them. And I do not have a list or anything like that, but parking structures are a good example of where concentrated loads may turn out to be important.
Okay, thank you, Dr. Just a minute. Should we consider dead load or self-weight while calculating the story drift for lateral load, like a combination of dead load and earthquake?
Yeah, this I addressed more than once. So your concern is interstory drift staying within tolerable limits. So the question is, does it make any difference how much gravity load you have sitting on your frame? And the answer is, unless you have a very significant lack of symmetry, the gravity load will not cause any lateral deflection, any appreciable lateral deflection. So whether you keep dead plus live on your structure or dead plus half of live, it doesn't really make a lot of difference when it comes to lateral reflections. So overwhelming majority of the time does not make any difference. However, if you have a distinct lack of symmetry, then dead and live loads may cause lateral deflections, and then you will have full dead load definitely considered. It's your judgment whether you want to consider full live load or one half of live load. Most structures never see more than a quarter of the design live loads during its lifetime. So if you keep 0.5 live load on your structure, that should be plenty. And that's what I think that those service load combinations were about. This is what it was trying to tell you.
Okay, so this is a big, long question.
Mm.
If live load reduction is assumed such that the whole panel loaded entirely is assumed, my question is why then load reduction is not allowed if the load is more than 100 psf? Because only 20% load can be reduced in that case. But if the load is less than 100 psf, then it can be reduced up to 40%.
It doesn't, I don't know that it has to do with the magnitude of the load so much as the heavy live load indicates occupancies where like heavy live load would be warehouses, libraries, and those things tend to be occupancies where most of the floor area will be covered, as opposed to lighter live loads where the live load is because of people sleeping or people dancing or people doing whatever. The exception is assembly live load. Assembly again means that most of the floor space may be occupied by people. Even then, if you calculate, the live load does not come to 100 pounds per square foot. It will have to be very heavy people really packed together to get anywhere near that. But the idea is that the logic behind live load reduction does not apply anymore. Almost the entire floor area can be fully loaded with design live loads in those situations. So this is why we do not allow heavy live load to be reduced. The logic behind live load reduction does not apply.
When story drift limit is not related to earthquake load, why time period is relevant in calculation of serviceability?
I didn't think it was relevant. I have a lot of problem with that. With the limitation in the BNBC. I honestly do not think it makes any sense. The period doesn't bother me as much as the fact that interstory drift limit is related to the total height of the structure. That does not make any sense.
Okay, this question has been answered. If in a 10-storied building, only one floor for only one floor, the live load exceeds 5 kilonewton per meter square, then can we take the live load factor as 1, or should we take the live load factor as 1 or 0.5?
The heavily loaded floor, it will be 1. For the other floors, it will be 0.5.
Yeah, you have to
Very simple.
consider it separately. Yeah.
Yeah, and it doesn't even have to be floor. It can be part of a floor that gets 1.0, and the remainder can be,
Doctor, this question I get in every webinar. Just can you just clarify? So a lot of participants they want like you to speak in Bangla. So I have told them a lot of times that you are more comfortable with English. So that is one thing.
Not that not that I'm more comfortable in English. Technical things come easier with English. I can be more exact in English. This is why I kind of stick to it. বাংলায় আমার বলে অভ্যাস নেই টেকনিক্যাল কথাবার্তা, কাজে আর আমি ওই ওই টার্মসগুলো অনেকগুলো জানি না, সেই জন্য অসুবিধা আর কি।
Right. Okay, I think most of the questions in the beginning we have answered. Is it necessary to consider the livelihood reduction factor?
No. It's entirely up to you. You know that is livelihood reduction is something permitted. So it is not something mandated. So if you do not take livelihood reduction, that is totally fine. Nobody, the building department will not find any fault with that. Your client may complain. You are spending more of his money for nothing. But it's not mandatory, no. Yeah, that's a good question.
Yeah.
Mhm.
So this guy is saying that in slide 44 mentioned that H is equal to total building height.
Say that again.
In slide 44,
Yeah.
H is that story height is total building height. That is what you have mentioned. I think that is what BNBC also says.
No, I quoted the H
Yeah,
is explained right there.
but he is saying that according to BNBC 1.5.6.1, H is the height of floor.
I quoted, I copied from BNBC. H is height of building structure, 1.5.6.1. I have it. I
But
can
according to BNBC, he is saying something. Yeah.
I can verify that. I have BNBC in right here. 1.5.6. Sorry.
That was one of the concerns that you were saying, right? Like,
Yes. I am looking at my BNBC copy. It says where H is equal to height of the building or structure. So I do not know if you have something different, maybe.
Actually, the BNBC 2020 gazetted version, Dr. Ghosh, it is saying height of floor, 1.5.6.1.
Okay, so that has changed, and I'm very glad to hear that that has
Yeah.
changed. Okay, that's a very good point that came out. I have the yeah. So this was corrected somehow in the gazetted version only. So I'm happy to hear that. Okay. So
Okay.
so I will correct that. Okay, let me make a note. But I read from my copy that was what was sent for guess. So then there was some correction made at a stage that I wasn't aware corrections were being made. This was slide 44. Okay. Okay, very good. Thank you for pointing it out. Okay, then I will have less criticism of this.
At least that is corrected.
Yeah,
So,
yeah.
okay. Lot of the questions related to quiz. Kindly mail to
The
support.
period,
Yeah.
let me explain the period. You know, although the earthquake period is being used, that is a little bit strange, but not by much. The idea is the period less than 0.7 of a second. Those are supposed to be rigid buildings, and the other ones are more flexible buildings, the longer period. So for the more flexible buildings, it's a tighter drip limit, which does make some sense. So I don't have a criticism of that. So if the H has been corrected, then it will be a significantly more sensible restriction.
Um, can we reduce roof live load for large industrial gable frames?
Large industrial gable frames roof live load. There is no restriction that I'm aware of. If you have a large area or slope, you can, but that 20 pounds per square foot cannot go below 12 pounds per square foot. There is a limitation. I'm saying our units, but anyway, the same limitation is in BNBC. You can reduce, but you cannot go below a certain value. You cannot take more than 40% reduction.
Is it permitted to assign partition wall loads as uniform loads, uniform pressure loads, I guess he's talking about,
We
instead
we
of line loads?
we typically deal with, that's what I was trying to point out. I apparently wasn't very successful. So movable partition load, I have never seen anybody doing line loads with them. So we take a uniform load of 15 pounds per square foot for movable partitions, and that number is 25 pounds per square foot in BNBC. But it is a uniform load that we take. Okay, not line loads. That's much more complicated. And that's what the last line was saying in BNBC. I forget which slide. It does tell you uniform load as a minimum uniform load of so much.
Can we use live load reduction for footings and foundations?
I do not know that anywhere we are told not to, and yeah, the whatever we have taken for the superstructure is carried down to the
Yeah,
foundation.
yeah. So you just have to
Yeah.
design for that. I think we went over most of the questions today, Dr. Ghosh.
Okay. Very good.
Yeah.
Okay. Thank you
Yes.
very much.
Uh,
Wayne, tomorrow. These are good topics. Now we are in a yeah. These are the big building blocks of design, understanding the loads.